Hi, everyone. Welcome to Hack on the Hill's Intro to Machine Learning workshop presented by ACM AI. My name is Nisha, and today Jason, Caden, and I are going to walk you through some of the theory of machine learning, as well as what you can do to apply it to your own hackathon projects. So this workshop is totally beginner friendly, which means a good place to start is what is machine learning. Take a second and think about some of the contexts where you've heard of machine learning and AI being used, or some of the ways that you've heard those terms being defined. Chances are you've probably heard a lot about machine learning and AI in the news because they're kind of dominating headlines. And that's for good reason, because AI and machine learning are really powerful and they can be used in pretty much any industry that you can think of, which means that our definitions for AI and machine learning are pretty broad. We say that AI is the theory and development of computer systems able to perform tasks that would normally require human intelligence. So those can be things like visual perception or understanding speech or making decisions. Again, super broad. And then machine learning is a subset of AI that provides computers with the ability to learn without being explicitly programmed. So we can picture a big bubble of AI that includes things like if-else statements and data mining and decision trees and Bayesian decision making. And then within that big bubble is a smaller bubble of machine learning. And that includes things like supervised and unsupervised learning, which we'll get into in a second. And also things like reinforcement learning, deep learning, if you've ever heard of that, and neural networks. So if you choose to work on a machine learning project, you'll probably follow this general pipeline. The first stage is to collect and pre-process your data, make sure it's ready to be used. The second stage is to actually build your model and train it to recognize patterns in your data. And the third stage is inference, where you actually get to put real data into your model and draw conclusions from it. So in this presentation, after we go through a bit of the basics of machine learning, Jason will talk about what you can do with your data, and Caden will talk about how you can build your model so that you're ready for the third stage by the end of the presentation. So we said we would get into supervised and unsupervised learning because these are really important topics within machine learning. So supervised learning means learning a function that maps an input to an output. And the way that we train our model is by feeding it input-output pairs or labeled data. Supervised learning can be a little bit tricky to grasp because in all of the math classes we've taken so far, we've probably gotten used to being given x and f and solving for f of x to get y. So we're given the input and the function and we're trying to solve for y. But with supervised learning, we're given the input and the output, so x and y, and we're trying to find the relationship or the f that maps x to y correctly. So if we look at an example, let's say we're trying to create a model that can take in an image and tell us whether it's a dog or a cat. So the way we would train our model with supervised learning is feeding in a bunch of images of cats and dogs and telling the model for each one whether the image is showing a cat or a dog. And then once we've finished training our model, we can test it out by giving it an image without the label, and our model will correctly identify that image as a cat. Supervised learning is really useful for regression and classification. So regression means that our output is continuous, something like price, or estimating final exam scores based on your input, which is your midterm and homework grades. And then classification means that your output is discrete, which means you're classifying between two or multiple classes. So classification could mean you're classifying a tumor as benign or malignant, or it could be the example we just looked at where you're classifying something as a cat or a dog. So the other type of learning is unsupervised learning, which is where we're learning patterns from unlabeled data. So with supervised learning, we were training on input-output pairs, but with unsupervised learning, you're just given the inputs. So this is what that same example would look like if we were doing unsupervised learning instead, we would still feed in all those images of the cats and the dogs, but this time we wouldn't label them. So we wouldn't tell our model, this is an image of a cat or this is an image of a dog. And so our model would output something that looks like this, where it is essentially telling you everything in the green circle is one thing, everything in the pink circle is some other thing. It doesn't know what a cat or a dog is, but it can tell you that all three images in the green circle share similar features, and those features are different from the ones in the pink circle. So with unsupervised learning, some of the tasks we can complete are clustering and generation. So clustering is where we split data into groups based on similarities, which is what we just did with the cats and the dogs. Clustering is also really commonly used for market segmentation, which is where a company wants to determine how to market its products and who to market which products to. And so it does that by looking at all of its customers and trying to figure out which customers have similar preferences and habits and would probably want to buy the same products. We can also do generation with unsupervised learning, which is where instead of classifying or categorizing our current data, we produce brand new instances of data. So new text or images or audio files that have never been fed into the machine. And an example of that is style transfer. So you can see in the image below, we fed in an image of the Mona Lisa, and our neural network was able to produce that same image, but in a bunch of different artists' styles. And so it's creating brand new data. So now we'll go into a couple of the algorithms that are really foundational to machine learning. The first one is linear regression, which is used in supervised learning specifically for regression. And the goal of linear regression is to find a line of best fits that models the universal relationship between several inputs and continuous outputs. So linear regression looks something like this, where you can see on the left, we have all these inputs and we're trying to find a red line that is closest to the pattern of the inputs. So in order to do this, we use the equation y equals w times x plus b, which looks a lot like the equation of a line we know and love. One thing to note here is that we are working with matrices. So w and x, for example, that's matrix multiplication, but this should still feel pretty intuitive, hopefully. Y is our output, x is the input, w is our weight matrix that determines the slope of the line, and b is our bias, which determines the y-intercept. So in doing linear regression, we're basically just adjusting the parameters w and b until we found the optimal line, which means that we've minimized our error. The other really important algorithm is logistic regression. And despite the name, logistic regression is actually used for classification. And the goal of logistic regression is to classify inputs into one of two categories based on the probability of each output. There's a little asterisk next to the 2 here because it can also be used for our multiple categories. For today, we'll just look at 2 categories. And this is what our equation would look like. So we have the same wx plus b that we had earlier. The difference here is that we're putting all of that into a sigmoid function. And what the sigmoid function basically does is take all of those values and bound them between 0 and 1 in a function that looks like the one on the left, which means that we're taking our output values and making them probabilities instead, so that we can determine whether our input is more likely to produce something of class 0 or class 1. And with that, I will hand it off to Jason to talk about working with data.
Okay, thank you for that, Nisha. Now that we've answered what is machine learning, it's time to turn our attention to data. If machine learning algorithms are the pans, whisks, and pasta makers of our data science machine learning kitchen, then data is our ingredients. Being the good chefs that we are, before we even fire up the stove or begin preheating the oven, we want to first thoroughly explore the data or ingredients that are available to us. 2, completely clean them. And 3, prepare them for cooking. All right, so enough of that analogy. Let's get into a kind of toy problem that'll help us understand these three things about the data exploration process. So let's say that you are a traveling salesman, or more accurately, you're a data scientist working for a travel agency. I just thought that this pun would be kind of funny. And your boss has asked you to select customers to receive a discount for their next hotel stay. And so you have some information about each customer, including whether they have previously received a discount. What type of problem is this and why? I'll give you all some time to think about it, but I encourage you, if you need more time, to pause this recording and reflect on what your answer might be. Right, so this is a supervised learning problem. More concretely, it's a supervised classification problem. And we say it's supervised because we are given historical data from which our model can learn and train on to make predictions about future unseen data. And we call it classification because we want to classify each customer as should receive discount or should not receive discount. First, let's get a sense of the data that we are working with. Let's assume that our data is in a comma-separated value or CSV file. And let's also assume that we're working with Python, which is a very popular programming language for data scientists and machine learning practitioners. There's an open source data analysis library in Python called Pandas, which when paired with Jupyter Notebooks, which is a fantastic feature of another Python library, makes parsing our data a piece of cake. So in our Jupyter Notebook, we run the above lines that I have on this slide to import the data. Note that I'm actually using something called Google Colab to generate these visuals, but I'll talk more about that on the next slide. For now, let's understand the data that we're working with. This is a totally synthetic file that I made up with just 3 lines of data, but working with this toy example can give us some things to think about when it comes to exploring our data. We can see that for each customer, we have what state they are based in, the number of months they've been a customer with the company, the average number of trips per year they take, their favorite destination, which I'll tell you, I mean to be their most frequently visited destination, their last trip, the date of the last trip, I should say, and the date of their last discount. Observe that in the third row for customer ID equals 2, there are some entries that say NaN, which is short for not a number and is typically read as NaN. What that means is that those values are missing in the original CSV file. So for customer 2, maybe we don't know how many trips per year they take because that value is just missing in the original customers.csv file. Can we think of some reasons why these values might be missing? And again, I encourage you to pause the recording and think of your response. Right, so customer 2 has only been a customer for 1 month. And so maybe they haven't gone on any trips yet, or maybe trips per year isn't recomputed until the end of each year. I'll tell you that I think it's more likely that it's the first option, since favorite destination and last trip are both NaN, indicating that customer 2, they've never gone anywhere before. And so maybe they've never taken any trips per year. And for whatever reason, in our database, we don't initialize that to a default value of 0. And so it's just missing. And now, as I promised, here's a brief aside on Jupyter Notebook and Google Colab. Jupyter Notebook is a web-based interactive computing platform. It combines live code, visualizations, and comments all in one place. And Google Colab is a platform for running those notebooks on Google servers with no local installation onto your machine required. I won't talk much more about this because it's not really the focus of this presentation. I just thought it'd be kind of useful to briefly mention, and I'd also recommend you to check out the interactive demo provided by Google at the link on the slide. That's colab.research.google.com. So what we're doing here on this slide is that we are using this code to import Seaborn, which is a data visualization library provided by Python, and then using Seaborn to plot a heat map that shows pairwise correlation between every 2 variables in a data set. And so this is one type of visualization we might create. And I should also note that this screenshot of a correlation heat map is not from the customers.csv file I made, since there are only 3 entries there. This is a screenshot from a previous data science project that I did. And I just think that this is more interesting to look at than the correlations for maybe a much smaller customers.csv file. And so looking at this correlation heat map can help us understand how the variables in the data set interact with each other. And so as we might expect, the really light values that indicate super high positive correlation, right? Correlation of 1, we see those along the diagonal. And that means each variable in our data set perfectly predicts itself. It's perfectly correlated to itself, and that makes sense. And on the opposite end, if it's a really dark, almost black value, then that means it is a really negative correlation between those two variables. And then the values that are kind of reddish in tone, those indicate maybe low correlation, like it's close to 0. Another thing we could do, besides looking at correlation heat maps, is to look at the histograms of each column in our data set. In this case, we're using a Python plotting library called matplotlib, which fun fact, Seaborn is actually based on. And these histograms give us a sense of the data distribution and scale for each column in our data set. And I'll use the term column and feature interchangeably because they kind of mean the same thing, but you can picture how each column in our CSV file in our data set represents a particular feature of our data set. Anyways, back to the histograms. We can see that the first 3 graphs show that they have a pretty skew right distribution. In fact, the one on the furthest left actually looks almost unimodal. There's just barely any points on the right side of the graph. And we can also see from these histograms that the range of these plots, right, for these different variables are different. So for the first 2, we can see that the values are ranging from 0 to about 30,000, whereas for the last feature, we have a range of maybe 0 to maybe a little bit less than 10,000 there. And so can anyone think about why we care about the distribution of our data? And to maybe get the gears turning in your head, let's say that we have a much larger customer data set. Maybe more realistically, we say we have 1 million customers. And so we have 1 million entries in our customers.csv file. And let's say that of those 1 million customers, only 10,000 of them have received a discount previously. How might knowing that information, how might knowing the distribution of customers who have received discounts be useful to us when we're building our machine learning model? And again, I encourage you to pause the recording and think about your answer. Right, so the answer is that because a relatively small fraction of our customers have received discounts, 10,000 out of 1 million, a classification model that is learning to classify customers as should receive discount and should not receive discount can trivially get pretty high accuracy just by saying no one should receive a discount, right? Because the majority of our customers don't. And so knowing the distribution of our data can help inform our decision about what types of data to include when we finally build our model, or even what kind of model we want to use. Another thing I want to mention is called principal component analysis, or PCA for short. This is a statistical technique that helps us determine which variables are most interesting based on their variance. For example, in this image on the right, we have a 2-dimensional scatter plot, and the arrows show us the principal components. And we can see that the arrow pointing to the upper right has a greater magnitude than the arrow pointing to the upper left. Or in other words, it's longer. And so this tells us that direction of the data is most important because it explains most of the variance in our data set. And so in this example for 2 dimensions, it might seem trivial. You probably could have looked at this even without the arrows and said, told me which direction has the most variance and is most interesting. But where this technique really shines is in higher dimensional. And again, that's equivalent to saying like more columns. So in higher dimensional data where we have maybe 10, 11, 12, 20, 30, however many columns you have where it's greater than 3, because I don't know about you, but I can't visualize what 20-dimensional space looks like. This is where PCA really shines, and it gives us a sense of which of those 20, 30, n number of columns, which of those are interesting to look at. And I won't go any further than that because it's not the focus of our presentation, going into technical detail, but I highly encourage you to check out this YouTube video I linked on the slide. You can just search it up, StatQuest Principal Component Analysis Step by Step. I think it is a really great introduction to the topic and explains it pretty succinctly, but also technically at the same time. Now, since I touched on it on the last slide, I want to briefly talk about scatter plots. Such diagrams can be particularly useful when you're trying to solve regression problems. And so, for example, maybe you want to predict the sales price of a house from its square footage. And creating this type of plot can inform our decision of what kind of model to fit to the data. And in this case, a linear model seems like it would perform decently. Now, besides these exploration techniques that I've mentioned, I would also like to mention that in larger projects, you might have access to data from multiple heterogeneous sources rather than just one source like the customers.csv file in our toy travel agency example. And so in that case, you need to examine each data source, understand what it offers, and determine if/how you would link those data sets together. And it's kind of up to you as the data scientist or machine learning practitioner to figure out what techniques make the most sense for your given data. It's kind of like when you're cooking, right? If you know that you're going to end up making brownies, you probably don't need to consider tomatoes. Like I can't think of a decent brownie recipe that uses tomatoes, so that's not something you have to look at. On the other hand, you should probably be focusing a lot on your choice of chocolate if you're going to make really good brownies. And so similarly for us as data scientists and machine learning practitioners, it's up to you to use your discretion to figure out, okay, this data doesn't seem so useful. This data I should probably pay attention to. And figuring out which of those things you should be paying attention to, that's the product of really good and thorough data exploration. So let's talk about data cleaning now. How do we deal with missing values in our data set? As we noted earlier, there are some missing values in our data set and the customers.csv data set, I mean, for customer 2, right? There's those missing values that are marked by nan. So how do we deal with these? The first of the techniques that I'll talk about is called imputation, and then we'll talk about deletion. Okay, so for imputation, there are 3 ways of doing this that I want to discuss. The first is called zero filling. And so what this is when we replace numeric values with 0, and when we replace categorical values with some reasonable default value. But I think more generally, I've seen it in the context of filling numerical values of 0. So for our toy data set, it makes sense to zero fill the missing trips per year for customer 2. As we discussed previously, it doesn't seem like they've taken any trips recently. And so, or actually at all, they haven't taken any trips of our company. And so we can reasonably infer that trips per year for them should be 0. Next, there is median / mean filling. And I want you to observe the new entry I created for customer 3. They have been with our company for 40 months, but their trips per year is missing. And because we can also see that they last took a trip in May 2018, we know they've taken at least 1 trip. And so it doesn't really make sense to say that their trips per year is 0. And so what we can do instead is take the median or mean value of the trips per year column and just say customer 3 has taken that median or mean trips per year. And our choice of either median or mean, that depends on the distribution of the data. So you can see how these processes of working with data, both data exploration, data cleaning, you can get a sense that they're linked. By examining those distributions, you can figure out, does it make more sense to use the median? Does it make more sense to use the mean? And work with that. And the last thing I want to talk about on this slide is mode filling. And that is when we use the mode or most common data point for a particular column. And so for this particular data set, maybe it makes the most sense to mode fill favorite destination if we don't know where a customer likes to go very frequently. And I know that there's not really a mode here because both Paris and Jakarta show up once. But it does make sense to use for categorical variables. And then there's deletion, which is kind of a last resort. And this is only for the case that we can't figure out how to reasonably impute those values using either of the techniques I mentioned, either zero filling, median mean filling, or mode filling. And the reason why this is a last resort is because less data generally means a less performant model. But if we have to do it, we can delete either rows or columns. And deletion of a row makes the most sense when you have a particular sample that has just a lot of missing values, or it just seems really wrong. Like let's pretend we have a customer who has been with the company for 400 months. That doesn't seem reasonable. So, maybe we can dump that. And I say that doesn't seem reasonable because, let's pretend that the company's only been around for 10 years. And so 400 months is way longer than 10 years. And so clearly that's wrong. Now, naturally, both imputation and deletion can be done with the pandas library. So now that we've explored and cleaned our data, it's time to select the features that go into our model. One thing we can do is drop features which we don't expect to have much predictive power. And so in the case of our customer's data set, we can probably get rid of the ID column because I don't think ID has anything to do with where a customer likes to go or how many trips per year they take. We can reasonably assume that those variables are independent of each other. And another thing we can do when choosing features is creating new features from existing ones. So in the case of our customer's data set, this could involve grouping together favorite destinations by country or even more coarsely by region. So instead of saying like, this customer likes to go to Paris, this customer likes to go to Jakarta, or I don't know, Washington, D.C., then maybe we want to group those destinations together to say these customers like going to destinations in North America or in Southeast Asia or Central America. And can anyone think about, maybe why we want to do this? Why we would group destinations rather than leaving them as is? Yeah, so the reason for this is, maybe there are way too many individual cities for our model to meaningfully learn anything from that. And so we could probably group by favorite country or favorite region, which, gives us a lot better sense of like how customers are related to each other. Because if we just tell a model that like, okay, this customer likes to go to Jakarta, just this customer likes to go to Surabaya, and those are both cities in Indonesia, the model doesn't know that they're both cities in Indonesia. And so it doesn't really gain anything from being told that those customers like to go to Jakarta and Surabaya. And instead, maybe we group it to Indonesia or even greater to the region level and say Southeast Asia. And so maybe some other things we want to do with these features is we could create a new column that is number of months since last received discount, because that is likely to be more informative to the model than just receiving the month and year of the last discount, right? We want to know how long ago was it that a customer received that discount. Okay, so going back to what I was talking about, like grouping those favorite destinations into country or region level variables, I guess, or labels, let's take a look at grouping them into continent level, which is really coarse, but it's all I could fit on this slide without it becoming unreadable. So even if we group our customers' favorite destinations into continents, we still have to figure out a way to encode them as numbers, because ultimately it's numbers that are going into our model. And so there are two ways that we could reasonably do this: ordinal encoding and one-hot encoding. In ordinal encoding, we just assign it a distinct number. You can think of it like a unique ID to each region in this case. So I said Asia has an encoding of 0, Oceania has an encoding of 1, all the way to Africa, which has an encoding of 5. On the other hand, we could do one-hot encoding, which is where we create a list of n elements, where n is the number of categories. And so in this case, we have 6 regions, and so n equals 6. And of those 6 elements, exactly one of them is 1 and the rest are 0. And so Asia, the one-hot encoding for Asia is 1, 0, 0, 0, 0, 0. And then for Oceania, it's 0, 1, 0, 0, 0, 0, and so on. And for this particular travel agency data set, I'm going to tell you that the one-hot encoding is the better choice for encoding this categorical information. And again, pause and think about it. Can you think of why one-hot encoding is better? Right, so an ordinal encoding scheme implies some sort of ordering or relationship between the different categories. And so our model might learn that Africa is in some way better than, greater than, more than Asia because it has a higher ordinal encoding, when I don't really think that's the case. And so we don't want to get our model to think that like, okay, there's this sort of ordering to the regions that I should be learning. So instead of one-hot encoding makes more sense here. Now here's an example where an ordinal encoding does make more sense. Let's say we add another feature to our data set called customer priority that goes from VIP to we forgot that they're even a customer. And so in this case, there is an ordering, right? VIP is clearly more important than customers who have high priority, who are more important than customers with average priority, and so on. And so in this case, it does make sense to have an ordinal encoding because we want our model to understand that there is a relationship between these categorical variables. Another data processing step for us to consider is data normalization. And some methods for normalization include min-max, mean, standardization, and scaling to unit length. In min-max normalization, we take the minimum value of the column and the maximum value of the column, and then we subtract from each data point in the column the minimum value, and then divide by the range, which is the maximum minus the minimum. In mean normalization, it's pretty similar, but instead of subtracting the minimum, we subtract the mean and then divide by the range. In standardization, we subtract the mean and then divide by the standard deviation. And in scaling to unit length, we divide each data point by its Euclidean norm. Note that data normalization is a must-do for some machine learning algorithms, while others will run fine without it. So for example, there's an unsupervised machine learning technique called k-means that attempts to find clusters in a data set by considering the Euclidean distance between points. And so you can think about how not normalizing our data would definitely have an impact on the solution that k-means arrives to, because if we don't normalize it, then the distances between features, different features will be different. And so maybe that's not something we want our model to learn. On the other hand, if we consider something like a decision tree classifier, which works by essentially doing a series of if-else comparisons, in that case, normalization makes practically no difference because it's just doing if-else, right? It doesn't really care about the magnitude of the data it's looking at. And again, I'm bringing up PCA, which is principal component analysis. Besides helping us to explore our data, it can also help us to choose features to use in our model. And so I think this is best explained by this picture I have on the slide, where maybe our data is initially in 3 dimensions, and we can see that there are 4 clusters that we maybe want to discover. This is not information you know beforehand. This is just for the visualization purposes that we have 4 clusters. But rather than examining the full 3 dimensions, we find that through PCA, we can actually reduce our data set down to 2 dimensions and still at least visually preserve those clusters. And they're still distinct. So our model might learn better from this because it does not have to consider as many dimensions, but it can still achieve decent results because, like I said, those clusters are still visually distinct. Of course, not all data sets are eligible for such a reduction. For example, you can imagine maybe in our 3D space, we have data distributed in a sphere. Then in that case, it's not really going to make sense to drop it down a dimension. But in many cases, reducing the dimensions of your data before feeding it into your model can be quite useful. And on that note, I want to mention that PCA is part of a broader set of techniques collectively called dimensionality reduction. And so another dimensionality reduction technique that you may want to look into after this presentation is called linear discriminant analysis. So now our data is ready to use in machine learning models, and you're almost ready to get back to your boss with which customer should receive a discount. And this was a lot of information, but what we hope you take away from this is that working with data usually is the lengthiest part of your project pipeline in any data science or machine learning project. And this is for good reason, because as we say in computer science, or if you haven't heard it said, now you're going to hear it, garbage in, garbage out, right? So if you're putting garbage into your model, you have really bad data, you're probably not going to generate any useful sort of predictions. And so you really want to spend time making sure that your data is cleaned, is imputed or deleted as necessary, formatted, processed, all that before you put it into your model. And so to avoid getting garbage out of our model, we want to spend lots of time ensuring we're not putting garbage in. And that wraps up the section of our presentation on, working with your data. And so now that you understand the tools for working with your data and you understand the sorts of machine learning algorithms that are available to you, as Nisha talked about, like linear and logistic regression, how do we actually build a model? And that's what Caden will talk about next.
Hello, everyone. I am Caden Davis, and I hope you have enjoyed our presentation thus far. Now we will launch into our final segment on actually building and deploying a machine learning model. So our first step is to select a model architecture or sort of its structure that we want to use. And the most important thing when we're choosing a model is the type of task that we are actually trying to complete. For example, if we have a continuous target variable, such as trying to estimate the price of a home based on some characteristics about it, this regression task lends itself very well to linear regression or multi-layer perceptron neural networks. This is pictured in the right-hand corner here, and this is a layer-based architecture that is very versatile. So it's core or fundamental to a lot of machine learning models. Classification, which is usually trying to take a piece of data and assign it to some category, is typically handled by logistic regression, or again, this is a task where multi-layer perceptron neural networks do very well. Clustering, which I know Nisha touched on a bit earlier, is when we take unlabeled data and try to partition it into groups. Most often, we will use k-means clustering as a choice of model for this task. K-means clustering takes data and partitions it into groups depending on its features, sort of separating them out into a vector space. It gets pretty math heavy, but that is something I hope you will learn to explore in the future. But yeah, then the model uses those partitions to determine which group new instances of data are most similar to, or which sort of region in space it falls under. But there are thousands of possible neural network architectures, each with pros, cons, and use cases for all types of input data. So there's no strict ruling for choosing one model versus another for different situations. Next, now that we have our model architecture, we need to teach it to sort of work on the actual data that we want it to be used for. When we train a model on a set of training data, we are essentially wanting it to learn the patterns of that data. And therefore, we call this process fitting the model, because it's teaching the model to make predictions based on those trends that it's learned from that training data. However, the extent to which our model fits the data is a bit of a balancing act. Seen here on the left, underfit models don't identify the major trends of data. They're too simplistic. And here on the right is sort of the opposite. Overfit models correspond too closely to our training data and are way too complicated or complex. Overfit models will therefore have high training accuracy, but when we present them with instances of new data, they won't be able to generalize well. Therefore, they will have poor real world and test accuracy. What we want is for something like this middle picture. This is called robust because it is able to generalize well, which is essentially, it's very versatile for many different types of data, not just what's in the training data, but it can extend it to new cases. And at the same time, it captures the major trends that we are trying to point out. It fits well. Generally, having too many epochs or having our model train on the training data too many times will lead to an overfit model. Having regularization methods is one potential way to help combat this. Regularization is a way to prevent our model from becoming too complicated by penalizing it as its complexity grows. This drives our model to be simpler and more robust, hopefully achieving something like the middle picture. Next, we need to validate our model to ensure that it's hitting the accuracy or performance metric that we are looking for. Validation is most typically done by partitioning a portion of our training data as test data or a validation set, which the model does not train on or ever see. Therefore, we can use the model's performance on this data to generalize how the model might fare when actually deployed. Having separate test data from our training data is pretty critical to avoiding overfitting. Another common technique is k-fold cross-validation. In this technique, we're going to iterate through our data, and each time we do so, we select a different portion of the training data as our validation set. We train on the rest of the data, validate our model's performance on the selected fold, it's called. This is just the portion that we've separated out. And then we average the performance at each of those iterations to estimate the overall performance of our model on real-world data. This technique is less popular than having a dedicated validation set of unseen or just untrained on data. But often when we don't have much data for our model to train on, we will use k-fold cross-validation because we don't lose any of that data. And if we don't have that much data to begin with, it's much harder to accept losing some of that data to create a validation set. Now that we have measured the accuracy of our model, at this point, we can either accept the model as ready for use or brainstorm ways to improve its performance. We might return to our data, exploring it further to see if cutting redundant data or adding new features will make our model more accurate. Or we can try to improve our model by tuning the model's hyperparameters. Hyperparameters are the manually adjusted aspects of our model. As an example, if our model has regularization, which again is a way to drive our model to be simpler and thus more robust by penalizing it as its complexity grows. We can tune hyperparameters by manually adjusting how strong that regularization effect is, that penalty term. Often though, it can be difficult to assess whether altering a hyperparameter will strongly benefit or harm our model's performance until we actually test it and see it for ourselves. So it can often be a matter of trial and error with tuning these hyperparameters. And that's everything we have to cover for our presentation today. Thank you all so much for attending, and I hope that you all have found a bit of interest in AI and machine learning and hope to explore it further. Building a machine learning model is often a cyclical process. First, we have to clean and process our data, create our training and test sets. Then we'll use that training set to initially train or fit a model. Then we will generate predictions for our validation data using that model. We will compare that to the ground truth or labels of our data to judge its performance. And this is typically when we are dealing with labeled data in supervised learning. But yeah, so we will typically use accuracy of prediction as our metric to judge model performance.